Hey everyone. Today, Grayson and I will be talking about gaming complexity and computing winning strategies, which are given a game state, will I win yes or no? Or can I win yes or no? Alright, so a game is defined as a form of play or sport, especially a competitive one, played according to rules and decided by skill, strength, or luck. But today we'll be talking about games that deal with skill more than the other two. So, games have been around forever. Historians believe games such as Mancala date back to 6000 BC, and I'm willing to bet there were plenty of games before that. So, even though these games have been around for so long, they still aren't easy to solve, right? Because if they were easy to solve, then no one would want to play them because you would just lose every time. Games are typically P-space or worse. So we won't really dive into what P-space is since that's another group's whole presentation. But games like tic-tac-toe, checkers, Connect 4, those you'll find in the P-space complexity, but they can get much worse than that, such as Magic the Gathering, which is speculated to be the most complex game in the world as of now. Yeah, we won't talk about Magic the Gathering. So the problem with these games is there are so many paths to look through and things to remember. Right? We can't lose any paths. We can't skip any, ignore any, because there's a possibility that those paths were the best one to choose. Um, and then we also have to order them from best case to worst case, uh, knowing like this is the best path to choose because it gives me the best chance of winning. But then there's other variables such as is the opponent even predictable, right? Are they even trying to win? Can we rely on them making the choices that we are hoping them to make? Or back to that best case, worst case scenario thing, maybe the best case is planning on them making a move at this specific spot, in which case we'll win. But if we don't know where they're going, maybe that's not the best move. I wouldn't know why, but maybe it's not. Um, yeah. All right. So the cool thing about this is many of these P-space games have been proven to be P-space complete. That means a quote unquote simple game such as tic tac toe could be used to solve all the problems in P space. So if there's an efficient solution for tic tac toe, then there's an efficient solution for everything in P space using tic tac toe, which is just funny. Um, Depending on if certain categories are equal or just subsets, then maybe tic tac toe can solve things in exponential time complexity, or maybe even harder than that.
Hi, everybody. So I'm going to start off by talking about the game complexity of tic-tac-toe. And so, as we all probably know, tic-tac-toe is a game played on a 3x3 board with two players, and the goal is for either player to get three of a row of their character on either a diagonal, a vertical, or a horizontal. And so, the possible number of game states in tic-tac-toe is going to be 3 to the ninth, and we get that number by the fact that there are three possible um, states that each cell on the game board can be in. It could either be empty, an X, or a 0. And then there's 9 states on the game board. So total game states, we get 3 to the ninth. But many of these are going to be illegal configurations because, for example, um, configurations with like 6 zeros or 9 zeros were included above, and those are obviously illegal configurations because that would have meant that the person who was playing for X never got to go, and that would be breaking the rules of tic-tac-toe. So if we delete all of these illegal configurations, we're left with only 500 or 5,478 configurations left, which is still quite a few, but a lot less than what we started with. And then as far as the possible number of tic-tac-toe games that could be played, that number is going to be 9 factorial, and we get that by the first move a person makes, they have 9 choices. The next move that's made, they have 8 choices, and there's only 9 moves as the upper bound of the number of moves in any game of tic-tac-toe. So the number of possible games, again, is going to be 9 factorial. But again, just like before we had a lot of illegal configurations, now we're going to have a lot of configurations that are redundant because they're either flips or rotations of another configuration. And so once we remove all of those flips and rotations, we're left with just 26,830 possible games. So piece-based games, as we kind of discussed earlier, are games that can be solved in a polynomial amount of space, or another way to say them would be, or say that would be that they have order O to the N, or sorry, big O, N to the K game states, where N is going to be the number of states that any position on the board could take, and K is the number of states on the board. So we can see, again, 3 was the number of configurations or states that any position on the board could be in, and there's 9 positions on the board in tic-tac-toe. So the game complexity of tic-tac-toe is big O of 3 to the K, and that falls into this class of piece bases. We have defined it here. Oh, so next I'm going to talk about a Turing machine for tic-tac-toe. And so this is going to be a 4-tape Turing machine, which is okay. It's going to be equivalent to some single-tape Turing machines, since we know that multi-tape Turing machines are equivalent to single-tape machines. And so the input for this Turing machine is going to be the input of a game of tic-tac-toe. So on each turn, which position did each player pick? And then the output for the game is going to be, since we're turning this into a decision problem, we're going to turn it into the decision problem. If we have players A and B, did player A win or did they lose? And so if we know, if it tells us player A won, then that means player B lost. And if it tells us player A didn't win, we know player B must have won. So I'm going to describe the 4 tapes now. So our first tape is going to be all of the possible moves that that each player could make from the current position of the game. And then tapes 2 and 3 are going to store the current positions that are covered by player A and B respectively. So tape 2 will store the positions covered by player A, and tape 3 will store the positions covered by player B. And then tape 3 stores all possible winning sequences of the game. And so kind of how this Turing machine works is it will compare tapes 2 and 3 to the final tape that has all of the winning configurations. And if one of those winning configurations shows up on tape 2, then that means the player for tape 2 won, and otherwise the player for tape 1 won. And again, this Turing machine uses big O of N to the K space, again, where N is the number of configurations each space in the game board can take, and K is the number of spaces on the game board. So here we're going to discuss a winning strategy for a tic-tac-toe configuration. So here we know that there is a winning strategy for X, which means no matter what the player for O does, if X uses the strategy, they're guaranteed to win. And so that strategy is going to go as follows, because the next turn is X's turn. I'm sorry, I forgot to mention that. So on the next turn, X will put an X in the top right corner of the board, and that will make it so there's no way for O to stop them from winning, because then on their next turn, they could either pick the one right below the one in the top right, or the one to the left of the one in the top right, and they would get a 3 in the row and win. So no matter what, they can win the game from this strategy, and we call that a winning strategy. Tic-tac-toe is actually a game that has a winning strategy for both players from the first move. So if both players use the winning strategy from the start, the best that either can do is tie, unless one other player, or unless the player you're playing against makes a mistake, you're guaranteed the best you can do is tie. If they tie, then you get an opportunity to win. So another topic that is related to this idea of game complexity is the min-max algorithm. And this is an algorithm that is a heuristic algorithm that's used to find the best decision to make from any turn that you're in a game. And so how this algorithm kind of works is we're going to represent the game as a graph. The final game states, so the winning, tying, or losing game states, are represented as leaves on the graph. And every other node represents another game state that's not a final game state. And then nodes are connected by edges if you can get from one node to another by just making one move in the game. And another important part about this algorithm is that each node in the tree will be assigned a value based off of some other heuristic, and these heuristics are specific to the game that we're using the min-max algorithm on. But basically how it works is, the max player is going to pick their max choice from the node they're on to any of the next nodes they could get to. They're going to pick the max choice, and the min player picks the opposite. They pick the min choice, and this end up actually being a pretty good heuristic for how to win a game.